Deep in our galaxy, a black hole named V404 Cygni erupts in violent bursts of X-rays bright enough to outshine entire star systems for a moment. What could cause such cosmic chaos? Tonight, we'll explore the mystery behind these explosive outbursts. If you enjoy this journey, please like, subscribe and share, and tell us in the comments, do you think black holes can ever truly be calm? Thank you for watching. Now let's begin. V404 Cygni lies hidden in the constellation of Cygnus far beyond what any human eye can see. Around it, the night sky appears calm, an ordinary scatter of stars across the northern hemisphere. Yet within this quiet region, space is not silent. Detectors on distant satellites record sudden waves of high-energy light arriving from the same point, flashes that appear and vanish in the span of minutes. They are X-ray bursts, each one a signature of an event too violent to be witnessed directly. The source, when traced through these bursts, is a binary system where a black hole draws matter from a nearby companion star. To observers on Earth, this region looks serene. To instruments built to measure invisible radiation, it is a place of recurring storms. Discovered in the late 20th century through irregular X-ray flares, the object first puzzled astronomers. Ordinary stars do not emit such rapid, erratic light. Each spike in intensity hinted at an origin compressed into a very small region, where gravity dominates every motion. Later analysis placed the system at a distance of about 8,000 light-years, within one of the Milky Way's spiral arms. That distance turns each recorded photon into a time capsule, carrying information from an era when early humans were shaping stone tools. The light from each burst began its journey long before language or memory crossing the thin dust of the galaxy to reach the detectors orbiting Earth. Seen in visible wavelengths, the surrounding field of Cygnus reveals nothing remarkable, no glowing nebula, no distinctive cluster. The black hole itself emits no light. Only through high-energy instruments does the system reveal its presence. Space telescopes capture periodic eruptions that rise sharply, peak and decay. These outbursts are not continuous. They come in unpredictable sequences separated by long stretches of calm. During the strongest flares, the system outshines the rest of the galaxy in X-rays, yet to the naked eye it remains dark. This contrast between quiet appearance and violent activity defines the character of the source, where energy alternates between storage and release. The pattern of emission provides a clue to scale. Because light cannot vary faster than it can traverse the emitting region, each burst gives an upper limit to size. Rapid fluctuations suggest a zone only a few 100,000 kilometers wide, far smaller than any ordinary star. Such reasoning led researchers to conclude that the source must contain a black hole. Later observations confirmed the presence of a companion star orbiting so closely that its outer layers are drawn away by gravity. The two bodies revolve around a shared center, locked together in a cycle of exchange. Material stripped from the star does not fall straight inward. It follows a curved path forming a thin stream that spreads into a rotating disk. Within this structure, friction between orbiting layers converts motion into heat, raising temperatures high enough to emit X-rays. The system's brightness comes from this process. Gas spirals inward, becomes incandescent, and releases radiation before crossing the unseen boundary of no return. The black hole itself remains invisible. What is seen are the consequences of its pull. In its quieter phases, the disk accumulates matter slowly. Over years, it grows dense and unstable. When a critical threshold is reached, the flow collapses inward, producing a sudden surge of energy, the kind that satellites detect as an outburst. Afterward, the disk cools and the system fades, returning to apparent stillness. Each eruption marks the conversion of stored gravitational potential into light, a transformation repeated across cosmic time. To measure such events, scientists rely on the most sensitive instruments in orbit. Each detector records the arrival time and energy of incoming photons, building a timeline of activity. From this data emerge light curves, sequences of peaks and dips that reveal how rapidly the source changes. By comparing these variations with models of accretion, researchers reconstruct the hidden geometry of the system. Even without direct sight, its behavior becomes traceable through patterns of brightness and decay. Locating the object precisely within the Milky Way requires careful geometry. Tiny shifts in apparent position measured as Earth orbits the Sun give its parallax and thus its distance. Radial velocity readings show that it moves with the galactic disk completing its slow orbit around the center of the Milky Way. In this way, the dark system becomes a mapped point pinned within the structure of the galaxy, though its form remains unseen. Each recorded flare is both event and message. The photons that reach Earth have crossed interstellar space largely unscathed, because X-rays pass through dust that would otherwise absorb visible light. This allows astronomers to monitor the system across decades, watching for cycles of brightening and decline. The bursts reveal the exchange of energy between a star and a gravitational well, between matter that shines and matter that consumes. From the broad field of Cygnus, the binary stands as a paradox motion without light destruction that produces illumination. It is both a location in the sky and a continuing experiment in physics played out beyond human reach. Instruments on Earth and in orbit remain tuned to it, waiting for the next sudden rise that will break the silence of the X-ray sky. In this steady observation, the system endures as a distant heartbeat, within the galaxy unseen yet persistent one, of the many hidden engines that shape the quiet light of space. V404 Cygni rests within the quiet fabric of the Milky Way, folded into one of its spiral arms that sweep around the galactic center like slow-moving rivers of stars. Its light, or rather the radiation that replaces visible light, travels through this landscape of dust and ionized gas to reach the detectors orbiting Earth. Mapping its place within this vast pattern requires patience, because the distances involved are measured not in the language of kilometers, but in the span of light years. Astronomers locate the system through parallax, the small angular shift seen as Earth circles the Sun. Against the backdrop of more distant stars, the position of the object shifts slightly, and from that shift comes distance. In the case of this source, the measurement places it around 8,000 light-years away, an immense gulf that turns every observation into a study of ancient light. Through this geometry, the system takes its position among the billions of other stars, one node in the wide spiral of the Milky Way's disk. The region of the galaxy that holds this system is neither rare nor crowded. It lies in the thin disk, a plain of gas and dust where most star formation occurs. The Milky Way's disk is about 100,000 light-years across and only a few thousand light-years thick. Within this sheet, young and old stars orbit the galactic center at different speeds, tracing slow ellipses. The black hole and its companion move as part of this flow, completing one orbit around the center, roughly every 200 million years. Their motion is calm, unhurried, following the gravitational curve that binds the galaxy together. Though the black hole releases energy during its bursts, these flashes are insignificant on the galactic scale. The surrounding medium absorbs and disperses them, returning the region to equilibrium almost as soon as they occur. In mapping such a system, astronomers use more than light alone. Spectroscopic studies reveal motion along the line of sight through the Doppler effect, the small shift in wavelength that depends on whether the object is moving toward or away from the observer. In visible light, the companion star shows these shifts as it orbits the black hole. its spectral lines sliding rhythmically back and forth. By measuring this motion, scientists calculate the orbital period about 6.5 days, and from that infer the mass of the unseen partner. The result is unmistakable. The object that draws on the star must be many times the mass of the Sun, yet compressed into a region smaller than Earth. No other known force or structure can produce such conditions except a black hole. Around this pair, interstellar space stretches in thin transparency. Clouds of hydrogen gas drift through the arm of the galaxy, forming delicate filaments under the influence of magnetic fields and gravity. These clouds act as both curtain and lens, absorbing some wavelengths while letting others pass. The radiation from the system travels through this medium softened but not erased. By analysing how different wavelengths are absorbed, researchers estimate the amount of material between Earth and the source. This measurement helps refine its distance and allows correction for the dimming caused by interstellar dust. The result is a clearer view not of shapes, but of signals. In a sense, studying this object is an act of translation, turning invisible radiation into understanding of motion, temperature, and structure. X-rays reveal the regions near the black hole, where gas is heated to millions of degrees. Optical light, faint but steady, comes from the companion star, a relatively ordinary object classified as a K-type star with a temperature of about 4,500 degrees Celsius. Radio waves trace the jets that sometimes emerge when the system erupts. Each wavelength tells a part of the story, and together they form a layered picture of interaction between gravity and matter. The placement of the system within the galactic disk also means that it moves through regions of varying density. Over millions of years, as it follows its orbit around the Milky Way, it passes through arms rich in gas and dust, then through clearer zones where only old stars remain. These migrations have little effect on the black hole itself, but may subtly influence the environment of the companion star, altering the flow of matter that feeds the disk. The balance between steady transfer and violent outburst may be shaped by these long cycles, though such effects are slow, unfolding over time scales far beyond human observation. When scientists map the galaxy, objects like this serve as reference points. Each binary system with a compact object, whether neutron star or black hole, adds to the chart of where such phenomena occur. Over time, a pattern emerges, many of them cluster within the galactic plane, often in regions that once hosted massive stars. This distribution supports the idea that black holes form from the remnants of massive stars after supernova explosions. The location of this one, deep within a spiral arm, fits that pattern. Its quiet presence is a trace of a much older event, a stellar death that happened tens of millions of years ago, leaving behind a collapsed core that continues to shape its surroundings. The Milky Way itself is not static. Its spiral arms drift, its stars migrate, and its gas clouds shift under gravitational tides. Within this motion, the black hole system remains bound to its companion, a microscopic detail in a rotating structure 200 billion times larger. Even so, the bursts that reach Earth remind us of its presence. Each X-ray flash marks a moment when energy confined for long periods escapes into the wider galaxy. From our position within another arm, we intercept only a fraction of that light, enough to study but not enough to see. In this way, the system exists both as a place and as a signal across time. It is fixed in coordinates but dynamic in behavior, visible only through the light it releases in moments of instability. Mapping its location within the Milky Way gives it context. It is not an isolated anomaly, but part of the galaxy's continuous cycle of creation and collapse. Stars form, shine, die, and sometimes leave behind remnants that continue to affect their neighbours. The object in Cygnus is one such remnant born from an ancient explosion, now quietly orbiting within the galactic disk and drawing matter from a living star. The two together form a small but enduring system moving along its orbit as the Milky Way turns slowly on its axis. In the scale of the galaxy, this binary is no more than a flicker yet to the instruments that watch it. That flicker carries profound information. The light curves and spectra gathered over decades define its position, not only in space, but in time. They allow astronomers to trace its movement, estimate its age, and fit it into the broader story of stellar evolution. Across thousands of light years, its X-ray bursts link the deep interior of a collapsed star to the outer edge of human knowledge, bridging distance with radiation alone. In the calm arms of the Milky Way, amid countless other stars, the faint pulses from this hidden source continue their long travel, announcing the presence of a gravitational well that still feeds on light. V404 Cygni sends its messages across the gulf of space as bursts of light too energetic for the eye to see. These signals travel for thousands of years before striking the sensitive surfaces of detectors that circle Earth. Each photon is a fragment of the system's history, carrying the mark of processes that occurred long before humans first turned metal toward the heavens. The light does not come steadily. It flares, flickers, and fades, forming a language of pulses that scientists have learned to read. When plotted as brightness over time, the result is a pattern of violent variability, brief eruptions followed by long silences. This irregular rhythm defines the object's character more clearly than any image could. For researchers, light itself becomes a tool to reconstruct what is hidden, because where vision fails, data remains. In the early years of X-ray astronomy, detectors aboard satellites such as Ginga and Swift revealed the restless nature of this source. The first observations came as sharp, unpredictable spikes in intensity. Unlike supernovae, which release one great outburst and then decline, this system flickers repeatedly, suggesting that its power is not the last act of a dying star, but the ongoing behavior of a persistent engine. The radiation arrives as discrete waves of energy, each corresponding to gas heated to millions of degrees near the black hole. Every surge marks a moment when material, after spiraling inward for years, finally crosses a threshold and releases its stored heat. The gaps between eruptions are periods of rebuilding when the disk cools and gathers new matter from the companion star. Interpreting these fluctuations requires a kind of astrophysical listening. Detectors translate incoming X-rays into electrical signals, which computers then record as time series data. When the system flares, the intensity can rise 100-fold in less than an hour. These rapid changes limit the size of the emitting region to something comparable in scale to a large planet far smaller than the Sun. By comparing the rise and fall of light across different energies, scientists estimate the temperature of the gas, finding values that reach tens of millions of degrees Celsius. At such extremes, atoms are stripped of their electrons, leaving plasma that glows in high-energy radiation. The brightness and speed of these flares show how quickly gravity can convert falling matter into heat. V404 Cygni's outbursts also vary across wavelengths. Alongside the X-ray flashes come optical brightenings and occasional radio bursts. This combination hints at multiple layers of activity in inner regions where gas releases X-rays, outer zones that emit visible light, and jets that project radio waves. During major events, the system becomes a multi-frequency beacon visible to a network of observatories. Each wavelength offers a different view of the same physics. When combined, they form a composite picture of the environment near the black hole, an environment that changes faster than any ordinary stellar process. The bursts are not random noise, they contain structure. Some show oscillations lasting seconds, others patterns repeating every few minutes. These quasi-periodic signals suggest that waves of pressure move through the accretion disk, modulating how gas falls inward. The inner regions may thicken and thin as heat builds and dissipates, creating pulses like a heartbeat. In this sense, the system breathes inhaling matter slowly and exhaling energy in bursts. Long after each flare ends, the X-rays continue to echo through the interstellar medium, their energies softened by distance but still detectable. Because the light from the system travels so far, what arrives on Earth is faint, but its variations are precise. By stacking many observations together, scientists can trace subtle cycles. Over decades of monitoring, they have learned that the system undergoes periods of dormancy lasting years, followed by weeks of explosive brightness. The largest outbursts in recorded history occurred in 1938, 1989 and 2015. Each time space observatories recorded rapid flickering that defied steady classification. The recurrence of these events shows that the mechanism is cyclical, controlled by how matter accumulates and then destabilizes in the disk. To capture such transient behavior, observatories coordinate across the globe. When a new flare begins, alerts travel between space-based instruments and ground-based telescopes. Optical, radio, and X-ray observations overlap to form a continuous record of the event. These campaigns turn the unpredictable into the measurable, allowing scientists to connect phenomena across different energies. The most detailed studies reveal that the X-ray light does not rise smoothly, but in chaotic jumps, suggesting that the inner disk may fragment under extreme conditions. Matter may pile up at certain radii before collapsing inward in avalanches, each one releasing a short flash of radiation. Even when the system quiets, traces of activity remain. In the low-state X-ray emission continues at reduced intensity, showing that accretion never fully stops. The disk still glows faintly, and the companion star's surface bears the imprint of heat from past outbursts. In this stage, the flow of matter becomes more ordered, forming a near-steady stream rather than bursts. The transition between these states, quiet and active, illustrates how small changes in the rate of accretion can lead to enormous differences in output. The delicate balance between supply and instability governs the system's entire life. Understanding the mechanism behind the bursts helps explain the broader behavior of similar black hole binaries across the galaxy. Many share this patterned, long periods of calm punctuated by sudden eruptions of radiation. In each case, the cause lies in how gas builds up in the accretion disk until it becomes unstable. When temperature and density reach a tipping point, viscosity increases, allowing matter to flow inward rapidly. The process releases gravitational energy as light, producing the observed X-ray flare. Once the inner disk empties, the brightness declines and the cycle restarts. In this way, the black hole's feeding resembles a heartbeat stretched across cosmic time. For Earth-based observers, each flare is a glimpse into physics that cannot be reproduced in laboratories. The forces near the event horizon are billions of times stronger than anything possible on Earth. Yet through the behavior of the light we can infer what happens there, how magnetic fields twist, how plasma rotates, how space and time curve together. Every dataset becomes a map of invisible motion, a translation of gravity into photons. The variations in brightness are not random flickers, but records of the changing flow of matter near the boundary of the black hole. Across the long arc of its existence, the system continues to emit these signals. They are faint, fast, and fleeting, yet persistent enough to build a continuous record stretching across decades. The sky may appear still to the eye, but behind that stillness is constant activity cycles of accumulation, eruption, and recovery. V404 Cygni embodies this hidden motion, reminding observers that even the darkest objects can announce themselves in bursts of light, With each new flare, the system reaffirms its presence in the galaxy, a source of power born from collapse sending its silent rhythmic messages through the long corridors of interstellar space. V404 Cygni exists as a pair bound by gravity, a black hole and a companion star locked together in a slow and endless exchange. Around their shared centre, both bodies orbit every 6.5 days, tracing paths so close that the larger star's outer atmosphere stretches toward its dark neighbour. The black hole's mass, about 9 times that of the Sun, pulls with such strength that the companion cannot hold on to its own material. Gas flows outward, not in a violent stream but in a steady invisible drift. What begins as faint loss at the edge of the star becomes the lifeblood of the system, a continuous donation of matter that feeds the unseen singularity. From this interaction arises the light that astronomers detect, the radiation that reveals the hidden engine of the system. In this binary, the ordinary star plays the visible role. Its orange surface glows at roughly 4,500 degrees Celsius, cool by stellar standards, but still hot enough to shine steadily across space. Yet it is not symmetrical. The gravity of the black hole draws one side outward, creating a subtle elongation that never relaxes. Tidal forces keep the star's rotation synchronized with its orbit, so that the same hemisphere always faces its companion. On that inner side, gas is lifted and pulled toward the point where the two bodies' gravitational fields balance. From there, the material begins its slow descent, crossing the invisible boundary that divides one star's domain from another's. As the gas passes through this narrow region, it accelerates, pulled onward by the black hole's gravity. But angular momentum prevents it from falling straight in. Instead, it curves around and begins to orbit, forming a flattened spiral that widens and heats as it rotates. This is the beginning of the accretion disk, the luminous structure that defines nearly every black hole binary. Within this disk, friction between adjacent rings of gas converts motion into heat. The outer regions glow in ultraviolet light, while the inner zones reach temperatures where atoms disintegrate, radiating X-rays that race outward into space. The disk becomes both a furnace and a barrier feeding the black hole, while releasing the energy of that descent as light. The exchange between the star and the black hole is steady but not constant. The rate of transfer depends on magnetic activity and the internal pressure within the companion's outer layers. Sometimes the flow thickens, sometimes it thins. Over long periods, the black hole's gravitational draw slowly strips the donor star, reducing its mass, while maintaining the orbit through conservation of angular momentum. The system adjusts to every change, its rhythm determined by balance rather than stability. It is a kind of quiet consumption that has likely continued for millions of years. Inside the disk, the motion of gas approaches a fraction of the speed of light. At such velocities, even small changes in flow create enormous variations in energy. Turbulence arises where temperature and density shift unevenly, and this turbulence drives magnetic fields that twist through the plasma. These fields act like invisible threads, transporting angular momentum outward and allowing material to drift inward. As matter spirals closer to the event horizon, each revolution brings greater heat and faster motion. The inner disk glows brightest just before the gas disappears from view. The radiation released there becomes the signal that satellites detect, the flicker that defines the system's identity. Though the star gives the material and the black hole consumes it, both influence the cycle of light. The donor star swells and contracts slightly, with each orbital phase changing the rate at which gas escapes. The black hole's gravitational field distorts the path of emitted light, bending it, so that photons from the far side of the disk still reach distant observers. Together, these effects produce subtle modulations in brightness, a repeating pattern superimposed on the chaotic bursts. Through careful measurement of these modulations, scientists deduce the orbital inclination, the size of the disk, and the relative masses of the two bodies. The data show a complex relationship, one of dependence and destruction, harmony and decay. The interaction between star and black hole is not purely mechanical, it shapes both over time. The companion loses matter faster than it can replace it through fusion, ensuring that one day it will become a smaller, fainter remnant. The black hole, though already immense, grows even more massive with every gram of gas that crosses its boundary. The disk, meanwhile, acts as an intermediary, transforming gravitational energy into radiation. What leaves the system as light and heat is a record of this process. Each X-ray burst corresponds to a moment when the flow of gas becomes unstable and collapses inward, converting mass into energy with remarkable efficiency. At larger distances from the center, the accretion disk merges gradually with the interstellar medium. The outflow of heat and radiation ionizes nearby gas, creating faint halos detectable in ultraviolet and optical wavelengths. These emissions trace the system's recent history, showing where older outbursts have heated the surrounding space. Over thousands of years, the region may expand into a bubble of thin plasma evidence of how even small binary systems can influence their environment. Beyond that halo, the energy dissipates into the general background of the galaxy, merging with the collective glow of billions of stars. In the quiet between eruptions, the system returns to a state of fragile equilibrium. The companion star continues to revolve, the disk continues to feed, and the black hole continues to pull. From Earth, instruments record only a faint, steady trickle of X-rays. Yet within that calm structure, heat and motion never cease. Pressure waves ripple through the disk like slow tides, rearranging matter and preparing for the next sudden instability. Each outburst begins long before it is seen, seeded by subtle changes that accumulate over months or years. The star's surface brightens slightly. The disk thickens, and deep inside, gravity waits. In this exchange, no sound is heard. No light escapes the final fall, and yet energy crosses the void to reach detectors on Earth. The black hole and its companion remain bound in their long orbit, continuing the cycle that began when one massive star collapsed into darkness and captured its surviving neighbor. The relationship is unequal, yet enduring a gravitational partnership that sustains both destruction and illumination. Observers who study the faint flicker of their shared light glimpse not only the physics of a binary system, but the quiet persistence of motion under gravity's rule. Hidden in the northern sky, the two bodies revolve the donor star, yielding its atmosphere, the black hole feeding silently, and between them, the disk turning glowing and vanishing into the dark. V404 Cygni continues its silent exchange, and from the steady flow of gas between the two partners arises a structure both delicate and immense, the accretion disk. It forms as material from the companion, star loses its hold and spirals inward, compelled by gravity yet constrained by its own motion. Instead of falling directly into the black hole, the gas spreads into a wide, flattened ring where each particle circles at extraordinary speed. Friction within the swirling plasma transforms motion into heat, and the disk becomes one of the brightest continuous sources of radiation in the galaxy. It is here within this incandescent spiral that matter reveals its fate long before it crosses the invisible boundary of the event horizon. The outermost layers of the disk are relatively cool, glowing in visible and ultraviolet light. Moving inward, temperatures rise sharply as friction increases and molecules break apart into atoms. Closer still, atoms themselves are stripped of their electrons, forming plasma that radiates in X-rays. The transition from cool gas to luminous plasma marks a continuous gradient of energy. Each region contributes its own signal, and together they create the broad spectrum of light detected from Earth. This disk is not solid. It is a turbulent flow of particles colliding, orbiting and sliding inward in a constant redistribution of angular momentum. Its edges blur into space while its core blazes with heat that no material could survive. At these extreme temperatures, magnetic fields emerge and twist through the disk like unseen threads. Generated by the motion of charged particles, these fields shape the flow of matter, channeling some of it outward and dragging the rest inward. In the dense inner zones, the plasma moves at a significant fraction of the speed of light. Small irregularities can produce immense differences in brightness, and the resulting flicker becomes the heartbeat of the system. For astronomers, these variations are not noise, but information signatures of shock waves, turbulence, and changes in the rate of accretion. The process is a slow collapse governed by conservation of energy. Every particle of gas that falls inward must shed some of its angular momentum, passing it to other particles through collisions and magnetic interactions. As this transfer continues, inner layers sink toward the black hole, while outer layers drift outward slightly. The energy lost in the process is released as heat and radiation. In this way, gravity's pull is translated into light, making the disk a luminous map of invisible forces. The closer matter comes to the center, the more energy it emits until the flow reaches the point beyond which light itself cannot escape. For scientists studying such systems, accretion disks serve as natural laboratories for extreme physics. They demonstrate how matter behaves in curved spacetime and how magnetic fields can grow from turbulence alone. Models built on data from V404 Cygni show that its disk extends several million kilometers across, yet its innermost edge lies only a few dozen kilometers from the event horizon. The energy density in this region surpasses anything else known in the universe outside supernovae and quasars. To understand its dynamics, researchers combine observation with theory, matching the timing and intensity of bursts to the equations of viscous flow and radiative cooling. Each comparison refines our picture of what happens near the edge of a black hole. From a distance, the disk appears stable, a symmetrical halo of radiation encircling an invisible center. In reality, it is restless. Pockets of denser gas form and dissolve, waves of heat propagate outward, and sudden instabilities can disrupt the entire structure. When a region becomes too hot, its pressure increases, pushing matter outward until it cools again. These fluctuations set the stage for the dramatic outbursts that define the system. Over months or years, the disk slowly accumulates gas, becoming thicker and hotter. Eventually, a threshold is reached where viscosity and heat combine to trigger a runaway flow toward the center. The inner zones collapse, releasing a torrent of X-rays before the process stabilizes once more. The geometry of the disk also plays a role in how its light reaches Earth. The system's axis is tilted relative to our line of sight, allowing observers to see both upper and lower faces of the disk at once. As the material orbits, Doppler effects shift the wavelengths of emitted light. One side appears slightly bluer, the other redder. By measuring these shifts, astronomers can calculate the orbital velocities of the gas and estimate the black hole's mass. The numbers confirm its extraordinary density, 9 solar masses confined to a region smaller than the planet Neptune. Around the disk, radiation pressure pushes against infalling gas, creating a delicate balance between outward light and inward gravity. This balance limits the maximum brightness of the system, known as the Eddington limit. When the accretion rate approaches this threshold, the disk becomes unstable, and excess energy may drive material outward in narrow streams. These outflows carry away angular momentum and help the disk maintain equilibrium. Some of the escaping gas may later fall back, forming secondary shocks that generate brief flashes across the electromagnetic spectrum. Each of these interactions contributes to the system's complex variability, turning a simple gravitational flow into a living dynamic environment. Even in quiet periods, the disk continues to evolve. Magnetic reconnection events where twisted field lines snap and rejoin release bursts of energy that ripple through the plasma. Such events can occur anywhere from the outer zones to the inner edge, producing flares that last from seconds to hours. Observers record these as irregular spikes in brightness, layered over the slower cycles of the larger outbursts. In this way, the accretion disk becomes a chronicle of continuous change, a structure where nothing remains still yet the overall form persists. Far from the disk, the effects of its heat extend outward. The intense radiation ionizes the surrounding interstellar medium, creating faint emission lines detectable by sensitive spectrographs. These lines provide a chemical fingerprint of the gas around the system, revealing traces of hydrogen, helium, and heavier elements expelled from the donor star. In some models, small amounts of matter are even blown away from the disk's surface by radiation pressure, forming a thin, high-velocity wind. This wind spreads elements into nearby space, linking the microscopic processes around the black hole to the larger ecology of the galaxy. At the human scale, such events are distant and silent, but at the cosmic scale they are part of an ongoing conversation between energy and gravity. The accretion disk of V404 Cygni stands as both engine and witness, transforming matter into light and returning that light to the galaxy that created it. Around the black hole, time flows differently, yet, across the vastness of space, its signals arrive in rhythm with our instruments, allowing us to watch a process that would otherwise remain hidden. The disk glows, cools, and glows again, a luminous veil around a place where light itself comes to an end. The disk surrounding V404 Cygni is not a tranquil structure. Within its glowing span, layers of gas move at extreme speed, building pressure, generating heat, and sometimes collapsing into sudden chaos. Here in the narrow region between order and instability, gravity and temperature engage in an endless contest. The gas flows inward as friction saps its energy, but magnetic fields and density variations resist the pull, creating turbulence that rises and falls like invisible weather. Over time, this internal conflict grows until it reaches a critical point, and the calm flow becomes unstable. The result is one of the most dramatic transformations in the system, the onset of thermal and viscous instability, when the disk begins to brighten and fracture from within. The outer regions of the disk accumulate matter slowly over months or years. As this material presses inward, the rising density traps heat, increasing temperature faster than the disk can radiate it away. At first, the energy escapes through radiation in ultraviolet light, but as the inner zones heat further, the balance collapses. Hydrogen, once partially ionized, becomes fully ionized, drastically changing how it absorbs and releases heat. The viscosity, the internal friction that governs how gas layers exchange momentum, rises sharply. A chain reaction follows. Heated gas moves inward faster, releasing more gravitational energy and creating more heat, which in turn accelerates the flow. Within hours, a stable disk becomes unstable, and the entire system shifts from quiet to eruption. During this transition, the structure of the disk changes shape. The innermost regions thicken, forming a hot inflated layer known as the corona. This region emits most of the observed X-rays, a storm of radiation produced by electrons accelerated to near-light speed. The corona surrounds the black hole like a halo of invisible fire, illuminating the disk beneath it. When instability begins, flashes of light ripple outward from the center. each representing a burst of energy released as new material falls inward. These flashes, seen from Earth as sudden spikes in brightness, are the moments when stored gravitational energy escapes as radiation. The physics behind this behavior lies in a delicate balance between heating and cooling. In the steady state, the heat generated by friction matches the energy radiated away. But as the accretion rate increases, the disk becomes optically thick, trapping its own radiation. Heat accumulates faster than it can escape and pressure builds. When pressure rises, the disk expands vertically, changing how it interacts with the surrounding radiation field. This further destabilizes the flow, driving mass inward at runaway pace. Within the span of a few orbits, material that had been circling for months plunges toward the event horizon. V404 Cygni's outbursts are a visible result of this internal chain reaction. The brightness can increase by hundreds of times as matter collapses inward. The X-ray luminosity briefly approaches the theoretical limit where radiation pressure balances gravity. During these periods, the system releases energy equivalent to the total output of thousands of ordinary stars. Yet the eruption is temporary. As the inner disk empties, less material remains to feed the black hole, and the brightness fades. What took months to build collapses in days, leaving behind a quieter, cooler disk that will slowly accumulate matter once again. The process repeats on a timescale defined by the rate of mass transfer from the companion star. Each new cycle begins as gas trickles in, forming a thin, dim disk. Over time, density and temperature increase until the conditions for instability return. This rhythm of accumulation and collapse gives the system its irregular heartbeat. From Earth's perspective, the pattern appears unpredictable, but in the physics of the disk, it is a natural outcome of how gravity, heat, and angular momentum interact. Astronomers study these transitions through changes in both brightness and spectrum. When the disk is cool, most radiation appears in the optical range. As it heats, the peak shifts toward ultraviolet and finally X-rays. The hardness of the spectrum, the proportion of high-energy photons, acts as a thermometer, showing when the instability has reached the inner zones. During a major outburst, the spectral shape changes rapidly, tracing the rise and fall of temperature within the disk. This provides a rare opportunity to watch an astrophysical system evolve in real time, transforming under its own internal dynamics. Magnetic fields play a quiet but powerful role in this process. As the plasma churns, differential rotation twists magnetic lines, storing energy like a coiled spring. When these fields reconnect, they release bursts of heat that can trigger or amplify instability. Some of the radiation observed during an outburst may originate from these reconnection events in the corona. They contribute to the erratic flickering that characterizes the light curve, especially in the early stages of eruption. Thus, what appears as random variation is in fact the combined result of many local instabilities interacting across the disk. The inner regions of the disk, only a few dozen kilometers from the event horizon, are the most violent. Here, the velocity of gas approaches the speed of light, and gravitational energy is converted to heat with maximum efficiency. The temperature can reach tens of millions of degrees, creating conditions where ordinary atoms cannot exist. Electrons and ions move independently, colliding at relativistic speeds, and producing high-energy photons through processes such as Compton scattering. Each photon carries away a fraction of the energy, escaping the gravitational field if emitted before the gas crosses the horizon. These photons, arriving at Earth thousands of years later, form the X-ray bursts that define the identity of the system. When the instability subsides, the disk returns to a cooler, thinner state. The corona contracts, the flow slows, and the light fades back to its baseline level. Yet the record of the outburst remains imprinted in the system. The the companion star exposed to increased radiation may lose mass more rapidly for a time, replenishing the disk and beginning the next cycle sooner. The interstellar medium around the system also bears traces of the event shock waves and ionization fronts that expand outward and gradually dissipate. In this way, each eruption leaves a faint echo in the surrounding space, evidence that the quiet of the galaxy is never truly still. The study of such instability has broader implications beyond this single system. It provides insight into the behavior of accretion disks around supermassive black holes in distant galaxies, where the same physics operates on much larger scales. By observing how matter behaves in this stellar-sized environment, scientists can refine models that apply across the universe. The patterns of heating, cooling, and eruption seen in this binary are miniature versions of the processes that power quasars and active galactic nuclei. The difference lies only in scale and duration. As V404 Cygni continues its cycle of calm and eruption, its light becomes a chronicle of energy transformed by gravity. Each outburst tells of a moment when balance failed and matter surrendered to collapse. Through its bursts, astronomers witness the raw mechanics of instability, a process that turns invisible forces into measurable light. Though the system lies thousands of light-years away, the information it sends remains clear, a reminder that even in the depths of space where darkness reigns, the smallest disturbance can ignite into brilliance before silence returns again. V404 Cygni reveals its nature most dramatically during moments of instability, when trapped material finally gives way and cascades inward in a rush of energy. These eruptions appear in data as sharp spikes, sudden leaps in brightness that last from hours to days. What occurs during those brief intervals is a complex sequence of physical reactions driven by gravity, pressure, and heat. The plasma that fills the accretion disk no longer moves in orderly spirals, but breaks into turbulent streams that plunge toward the event horizon. The system becomes a theatre of forces operating at their limit, where matter is stripped of identity and transformed into radiation. This transformation, the conversion of gravitational potential into bursts of X-rays, is what astronomers describe as the outburst phase, the moment when the black hole's hidden activity becomes visible across the galaxy. During an outburst, the inner regions of the disk radiate with nearly continuous brilliance. Temperatures climb to tens of millions of degrees, and the light emitted spans from ultraviolet to hard X-rays. The emission fluctuates rapidly, indicating that the process is not smooth, but composed of many overlapping avalanches of gas. Each avalanche begins when a packet of material destabilized by heat or magnetic reconnection loses its remaining angular momentum and plunges inward. As it falls, it compresses, generating even more heat and releasing enormous energy in the form of photons. To observers, the combined effect appears as flickering brightness with peaks that rise and fall in seconds. The scale of energy release is vast. In its brightest moments, V404 Cygni can radiate more power in X-rays than the entire output of the Sun in all wavelengths. Yet this energy does not come from nuclear fusion, but from gravity itself. When gas falls into a deep gravitational well, a portion of its rest mass is converted into energy following the principles of relativity. This mechanism makes accretion onto black holes one of the most efficient energy processes known in the universe. Each burst recorded by telescopes is thus a direct expression of Einstein's equation in action. Matter transformed into light at the edge of a region where light itself can vanish. The outburst does not occur in isolation. The sudden increase in radiation pressure can disturb the disk and drive winds outward. These winds carry material away from the inner region, forming thin streams that race into space at thousands of kilometers per second. Some of this matter escapes entirely, while some eventually slows and falls back, striking the outer disk and producing secondary flashes. The system becomes self-interacting, a feedback loop where each eruption triggers new disturbances. The companion star also feels the effect its surface is heated by the flood of radiation, which may alter the rate at which it donates gas. In this way, a single outburst can reshape the balance of the entire binary for years afterward. Scientists record these events using instruments that can respond quickly to sudden changes in brightness. Satellites such as Swift and Integral continuously scan the X-ray sky, ready to pivot toward any new flare. Once the system brightens, a chain of observations begins: X-ray, optical, infrared, and radio telescopes all focus on the same target, capturing data across the electromagnetic spectrum. From this combined view, astronomers can reconstruct the timeline of the outburst: the first surge of heat from the inner disk, the expansion of the corona, the ejection of matter, and finally the gradual decline as the system cools. The detailed light curves serve as fingerprints of the processes at work near the black hole's boundary. Within hours of the eruption's onset, the disk transforms into a highly luminous and unstable structure. The inner zones become dominated by radiation pressure rather than gas pressure, making them more susceptible to oscillations. These oscillations manifest as quasi-periodic variations in the X-ray intensity, subtle pulsations that repeat every few seconds. The origin of these oscillations remains a subject of study. They may arise from waves travelling through the disk or from the precession of the inner regions distorted by the black hole's spin. Whatever their cause, they offer a glimpse into dynamics that occur within a region only a few dozen kilometers wide. As the outburst progresses, energy begins to flow outward as much as inward. The magnetic fields that thread the disk can funnel some of the infalling matter into narrow jets that shoot away from the poles of the system. These jets travel at relativistic speeds, emitting radio and gamma radiation as particles accelerate along their paths. In this phase, the black hole becomes both consumer and creator, devouring gas through one channel while expelling energy and matter through another. The balance between inflow and outflow determines how long the outburst lasts. When too much mass is expelled, the inner disk starves and the system fades back to quiescence. During the decline, the light curve softens. Hard X-rays give way to softer emissions and the spectrum gradually returns to its pre-eruption shape. The corona contracts, the jets weaken, and the disk cools. This stage can last weeks, with brightness decaying smoothly as the reservoir of infalling gas is exhausted. Eventually, the system returns to its quiet state, releasing only faint X-rays produced by slow, steady accretion. From Earth's perspective, the dramatic flare subsides into silence, leaving behind only a memory encoded in data. The aftermath of an outburst is as important as the event itself. The surrounding interstellar medium, heated and compressed by radiation, and particle winds, forms temporary structures that drift outward. Over centuries, these subtle effects contribute to the chemical and energetic texture of the galaxy. Within the system, the black hole's mass has grown slightly. The companion star has lost more of its atmosphere, and the disk begins to rebuild from the remnants of the last eruption. The cycle restarts, guided by the same forces that shaped it millions of years ago. For scientists studying these violent transformations provides insight into the universal mechanisms of accretion. The same physics governs systems of vastly different scales, from binary stars to quasars, billions of light-years away. V404 Cygni, though only a few solar masses in size, serves as a microcosm of cosmic activity. It allows researchers to observe in days what might take centuries in larger systems. Each eruption is a replay of processes that illuminate galaxies, drive jets from supermassive black holes, and shape the radiation landscape of the universe. The sudden X-ray outbursts of this binary system are reminders that even in deep time energy never rests. What appears as a distant flicker in the data is in truth the transformation of matter into pure light governed by gravity and the immutable laws of motion. In each pulse, the black hole speaks through radiation, a voice carried across thousands of years to reach our instruments and reveal its momentary fury. When the flare fades, only darkness remains, yet beneath that darkness, new matter is already gathering, preparing for the next release. The rhythm continues unending, an exchange of silence and brilliance that defines the life of a black hole and the fragile star that orbits it. When V404 Cygni erupts, the energy released does not remain confined to the disk. From regions near the event horizon, streams of charged particles burst outward in opposite directions, forming what astronomers call relativistic jets. These jets are among the most powerful and striking phenomena in astrophysics, narrow beams of plasma propelled at nearly the speed of light. Though they carry only a fraction of the matter spiraling inward, their influence extends far beyond the binary system. They illuminate space across multiple wavelengths and reveal the intimate connection between gravity, magnetism, and energy. In V404 Cygni, these jets appear as sudden outflows that accompany major X-ray flares, linking the quiet inflow of accretion to the outward violence of ejection. At the base of each jet lies the corona, the region of superheated plasma surrounding the black hole's inner disk. Within this zone, magnetic fields are twisted and amplified by rotation, creating the conditions necessary to launch matter outward. The mechanism is still being studied, but it likely involves the extraction of rotational energy from the black hole itself or from the disk that orbits it. When field lines reconnect or align along the rotational axis, they accelerate particles to relativistic speeds, collimating them into narrow beams. These beams punch through the disk's outer layers and continue into interstellar space, carrying radiation that can be detected long after the initial flare fades. For observers on Earth, the appearance of jets marks a dramatic shift in the system's behavior. During outbursts, telescopes detect not only X-rays but also bursts of radio emission, a telltale sign that electrons are being accelerated to high energies and spiraling along magnetic fields. As the jets expand, they cool and emit synchrotron radiation, producing a glow that lingers for days or weeks. The brightest radio burst from V404 Cygni have revealed structures extending billions of kilometers, proof that these streams move outward at nearly the speed of light. Even as the accretion disk fades from view, the jets remain visible, carrying energy far from the central source. The creation of jets involves a paradoxical balance. Gravity draws matter inward, while magnetism drives part of it outward. The two forces operate simultaneously, forming a feedback loop, where the same flow that feeds the black hole also generates its outward beams. The strength of the jets depends on the spin of the black hole and the configuration of the magnetic fields anchored in the disk. In V404 Cygni, the black hole's rapid rotation likely enhances this process, allowing it to fling material across interstellar space with extraordinary efficiency. The result is a system that alternates between feeding and expelling a cosmic engine that converts infalling mass into kinetic power. Jets do more than release energy. They shape the space around them. As they plow through the surrounding gas, they create shock waves that compress and heat the interstellar medium. Over time, this process carves cavities and filaments visible in radio and infrared maps. Although the total energy involved is small compared to that of galaxies, It demonstrates how even a single stellar mass black hole can influence its environment. These effects are scaled-down versions of the vast outflows seen in quasars, proving that the same physical laws govern systems from a few solar masses to billions. Observations made during the 2015 outburst of V404 Cygni offered an unprecedented look at this process. Space-based and ground-based instruments worked in coordination, recording the rapid alternation between inflow and ejection. Every bright X-ray spike was followed by a delayed radio burst, a signature that jets had formed as the inner disk emptied. Images taken with very long baseline radio arrays showed distinct knots of emission moving outward from the system, expanding over time, as if launched from a cannon of magnetized plasma. By tracking their motion, scientists determined that the material in these jets was moving at more than half the speed of light, a velocity that requires immense acceleration over distances no greater than a few hundred kilometers. Within the jets, particles experience extreme conditions. Electrons spiral along magnetic field lines, emitting synchrotron radiation as they accelerate. The resulting light spans from radio waves to gamma rays depending on the energy of the particles and the strength of the fields. Near the base of the jets, where densities are highest, collisions between particles produce additional high-energy photons, further enriching the system's emission spectrum. This diversity of radiation allows scientists to probe the jets at different stages of their evolution, compact and bright, near the source diffuse and fading as they expand outward. The persistence of these jets long after an outburst has ended suggests that they play a stabilizing role. By carrying away angular momentum and excess energy, they may help the disk return to equilibrium more quickly. Without such outflows, the inner regions could overheat or become even more unstable, leading to prolonged chaos. Instead, the jets act as release valves, allowing the system to balance the opposing pressures of accretion and radiation. Once the energy reservoir is depleted, the beams fade and the black hole returns to its quiet state, awaiting the next build-up of material. For astronomers, the study of these phenomena provides crucial insights into the link between magnetic fields and gravity. Though jets are seen in many systems from young stars to galaxy cores, their origin remains one of astrophysics' central questions. V404 Cygni offers a nearby laboratory where the process can be observed in detail. Because the system lies within our galaxy and erupts on human timescales, it allows repeated observation of how matter behaves in extreme environments. The data gathered here inform models that apply to objects millions of times larger, connecting the smallest black holes to the most massive known in the universe. As the light from each eruption fades, the remnants of the jets continue their journey through space. Their particles, now far from the system, eventually slow and merge with the surrounding medium. In doing so, they contribute to the faint background glow of the galaxy, enriching the interstellar gas with energy and elements. The process is imperceptible on human timescales, but significant over cosmic durations. It shows that even an isolated binary system can leave a lasting imprint on its surroundings, linking the story of one star's death to the evolution of the Milky Way itself. The jets of V404 Cygni thus stand as outward expressions of the same gravitational forces that make the system invisible at its core. From collapse comes release, from inward fall, outward flight. These twin motions, accretion and ejection, define the black hole's existence, sustaining a rhythm that has continued for millions of years. Each time the system flares, the balance between them is briefly revealed, and the universe records another instance of matter transformed into light, motion, and heat. Across the depths of interstellar space that light reaches our telescopes, a fleeting reminder that in every act of consumption the cosmos also creates. V404 Cygni hides at its center a boundary that defines both the mystery and the power of the system, the event horizon. Beyond this invisible surface, gravity is so strong that nothing, not even light, can return. The horizon is not a physical wall, but a region in space-time where escape becomes impossible. All paths curve inward, drawn toward a singularity that marks the ultimate collapse of matter. Around this center, every motion, every flicker of energy recorded from Earth finds its origin. The accretion disk, the jets, the bursts of radiation, all are the outer manifestations of what happens as matter approaches that boundary and vanishes. For astronomers, the event horizon represents both an end and a beginning, an end to visibility, a beginning to knowledge inferred through light emitted just before disappearance. The black hole in this system has a mass about 9 times greater than the Sun, yet it occupies a region no wider than a few dozen kilometers. This concentration of mass creates an escape velocity exceeding the speed of light, producing the gravitational well that defines the event horizon. Matter approaching this region experiences a steep gradient in gravity, a tidal force that stretches it along one axis and compresses it along another. These forces grow exponentially stronger with proximity to the horizon. As particles spiral inward, their orbits quicken, releasing energy that heats the surrounding plasma to incredible temperatures. The radiation we detect originates not from inside the horizon, but from this last region of violent compression where matter makes its final stand against gravity. At such proximity, the normal geometry of space and time ceases to behave intuitively. Time slows relative to distant observers, and the paths of photons curve under gravity's pull. Light emitted from the inner disk does not travel in straight lines. It bends around the black hole, creating optical illusions of distorted rings and arcs. In theoretical images, an observer facing the system would see the top and underside of the disk simultaneously, the far side's light deflected over the horizon's edge. This gravitational lensing allows us to perceive aspects of the system that would otherwise remain hidden. Although no telescope can yet resolve these features in V404 Cygni, they are confirmed in principle by the physics observed in larger black holes, including the one at the center of our galaxy. The region immediately outside the event horizon, called the innermost stable circular orbit, marks the last place where matter can revolve without plunging inward. For a black hole of this mass, that orbit lies only a few tens of kilometers from the singularity. Within this narrow band, orbital periods last milliseconds and speeds approach half the speed of light. Each particle circles thousands of times before crossing the point of no return, releasing vast amounts of energy as friction and radiation. The light that escapes from this region is highly redshifted, its wavelength stretched by gravity as it climbs out of the well. This gravitational redshift is one of the key indicators of how close the emitting gas lies to the event horizon. Because the black hole itself emits no light, scientists must study its environment to understand its properties. By observing how matter moves near the horizon, astronomers estimate the black hole's spin, a measure of how fast it rotates. Evidence suggests that the black hole in V404 Cygni spins rapidly, possibly completing several rotations each second. This spin drags space-time itself, twisting nearby magnetic fields and influencing how jets are launched. The coupling between rotation and magnetism is thought to power the outflows seen during eruptions, allowing some of the black hole's rotational energy to escape into the surrounding universe. Thus, even though nothing can cross outward through the horizon, energy can still be transferred indirectly through these interactions. The environment near the horizon is a realm of extremes. Temperatures reach tens of millions of degrees, magnetic fields intensify to billions of times Earth's, and time itself becomes distorted. For an infalling particle, the journey from the disk to the horizon takes only milliseconds, yet to a distant observer, the same particle seems to slow and freeze at the boundary. Its light, stretched into longer wavelengths, fades until it disappears entirely. In this way, the event horizon acts as both an absorber and a mirror swallowing matter, while preserving its final image in the form of fading radiation. The photons that escape at the last moment carry the history of everything that falls inward. Although we cannot see inside the horizon, the mathematics of general relativity describes what happens beyond it. All matter and energy converge toward the singularity, a point where density and curvature become infinite. Current physics cannot describe this region. The known laws break down. It represents the edge of human understanding where gravity must merge with quantum mechanics to form a complete theory. V404 Cygni, like all black holes, embodies this frontier and natural experiment that reveals the limits of what we can observe and calculate. Despite its invisibility, the black hole leaves a measurable imprint on its surroundings. The companion star's orbit traces the unseen mass, the disk's emission follows predictable gravitational patterns, and the timing of flares corresponds to processes near the inner orbit. From these clues, scientists build a coherent picture of a region that can never be directly photographed. Each dataset, each spectrum becomes a sketch of the horizon's invisible contour. Through careful modelling, astronomers can even infer how the black hole's gravity warps the path of light from the companion star, producing subtle variations that match theoretical predictions. The study of V404 Cygni thus connects observation with theory in a way few other systems can. It allows physicists to test general relativity under extreme conditions, to measure the relationship between spin mass and energy release, and to explore how magnetic fields operate in curved spacetime. Each X-ray flare, each radio burst offers another test of how well our equations describe reality at its most intense. The fact that these predictions match what is seen gives confidence in the theory, while the remaining discrepancies point to the mysteries that still lie beyond it. At the heart of the system, the event horizon remains unseen but ever active, swallowing gas, bending light, and shaping the flow of time around it. The material that crosses this threshold is lost forever from the visible universe, yet its approach announces itself through light that travels for thousands of years to reach us. The photons that escape just before the fall are the system's final words, carrying information from a place where information itself comes to an end. As long as the companion star continues to feed the disk, this process will continue a slow, steady sacrifice that sustains the glow of the unseen. In the silent depths of Cygnus, the black hole endures its presence defined not by what it reveals, but by what it consumes. At the very edge of the black hole in V404, Cygni, the fabric of reality, bends so steeply that time and motion no longer behave as they do elsewhere. Within a few dozen kilometers of the event horizon, every atom and photon is caught in an environment where gravity distorts the passage of seconds and stretches the path of light. This innermost region where matter completes its final revolutions before vanishing forms the heart of the system's energy. Though invisible, it is the source of every signal that reaches Earth. The flicker of X-rays, the hum of radio waves, and the faint afterglow of light released from matter in its last moments. The boundary between visibility and oblivion is thin, measured not in distance but in gravity's intensity, where the universe's laws meet their limits. In this extreme domain, space and time intertwine. A particle orbiting the black hole experiences seconds that stretch into minutes for an observer far away. What to us appears as a gradual descent toward the horizon is for the falling particle an instant. This disparity arises from gravitational time dilation, a phenomenon predicted by general relativity and confirmed by the behavior of light near massive objects. The closer a particle moves to the black hole, the slower its clock runs relative to the outside universe. For an observer on Earth, matter seems to freeze just above the horizon, dimming and fading as its light redshifts into longer wavelengths. Yet in the frame of the infalling matter, it continues inward, crossing the boundary in finite time. Both perspectives are correct, their contradiction resolved only by the curvature of space-time itself. The inner edge of the accretion disk lies close to the innermost stable circular orbit, a region governed entirely by relativity. Here, gas travels at more than half the speed of light-tracing spirals that complete thousands of revolutions per second. Small differences in velocity lead to immense shear heating the plasma to tens of millions of degrees. Magnetic fields twisted by this rotation form loops that connect the inner disk to the corona above it, transferring energy in bursts that may trigger the observed X-ray flicker. These magnetic arcs behave like stretched rubber bands, snapping and reforming in cycles that release stored energy as radiation. In this interplay between rotation, magnetism, and heat, the inner disk becomes a self-sustaining engine of light. To study these processes, scientists use spectral and timing analysis. The shape of the X-ray spectrum reveals how energy is distributed among particles, while the timing of fluctuations shows how quickly conditions change. From this data, models emerge that describe the corona as a region of electron clouds scattering photons from the disk. Each scattering increases the photon's energy, creating the hard X-rays that dominate the system's brightness during eruptions. The corona's structure is not fixed. It expands and contracts depending on the flow of matter and the power of the magnetic fields. During quiet phases, it shrinks close to the event horizon, while during outbursts it swells, extending far above the disk like a glowing atmosphere. Near the horizon, gravity influences not only the flow of matter, but the path of light itself. Photons emitted inward can orbit the black hole several times before escaping, creating echoes that stretch and blur the signal detected far away. This effect produces characteristic patterns in the light curve known as reverberation lags, small delays between changes in the inner and outer emission. By measuring these lags, astronomers can estimate the size and geometry of the region producing the radiation. In V404 Cygni, the time delays are measured in milliseconds, indicating that the X-rays originate from a region only a few dozen kilometers across, confirming the extreme compactness of the system. Another consequence of curved space-time is the gravitational bending of light from the companion star and outer disk. Photons passing near the black hole follow curved paths, altering the apparent brightness and position of features around it. These distortions, though imperceptible to the human eye, can be extracted from high-precision data. They allow researchers to reconstruct the shape of the inner environment with remarkable accuracy. Through this technique, the invisible becomes partially visible, not as an image, but as a map derived from the way gravity manipulates light. As matter falls toward the event horizon, it releases almost all its remaining potential energy. A fraction of this energy escapes as radiation, while the rest disappears beyond detection. The efficiency of this process depends on the black hole's spin. Faster rotation allows material to orbit closer to the horizon, extracting more energy before crossing it. Estimates suggest that the black hole in V404 Cygni converts nearly 10% of the infalling mass into radiation, a rate far higher than any nuclear reaction. Each X-ray photon we detect represents a triumph of light over gravity, a trace of matter's last resistance before annihilation. Within the final orbits, matter behaves less like gas and more like a fluid of energy. Magnetic fields dominate, turbulence becomes extreme, and time itself loses clear meaning. In simulations, this region resembles a boiling surface, where plasma flows along contorted field lines, alternately heating and cooling as energy escapes. The precise structure cannot yet be observed, but the theory is supported by the flickering patterns seen during major outbursts. These variations correspond to changes in the inner flow, evidence that even near the edge of the event horizon, dynamic processes continue to shape the emitted light. For an observer within this region, if such an observer could exist, the outside universe would appear to accelerate and brighten as the fall continued. Light from distant stars would be blue-shifted, compressed into higher energy, until all directions glowed with the distorted image of the sky. Then, as the horizon was crossed, external light would fade, leaving only darkness. For the outside world, however, that crossing never occurs, the object's image remains frozen forever, its light redshifted beyond detection. The boundary thus becomes a kind of mirror reflecting both our limits and our curiosity. From Earth's perspective, all that remains visible is the radiation emitted in those final moments before disappearance. It is this light that instruments record transforming mathematical theory into observation. Each detection confirms the predictions of relativity, yet each also points to questions that remain unanswered: how matter behaves once it crosses the horizon, how quantum effects might alter the nature of the singularity, and whether information truly vanishes inside. These mysteries ensure that the black hole is not merely a sink of matter, but a continuing source of discovery. In the story of V404 Cygni, the inner region is both the furnace and the frontier. It is where light is born from falling matter, and where light itself begins to die. Everything observed in the system, every flare, jet and burst, originates here within a few dozen kilometers that contain more energy than an entire star. Though this domain will never be directly seen, its existence is made clear by the signals that reach us across time and distance. Each photon that arrives carries a record of the last interaction between energy and gravity, the last trace of matter before it becomes part of the black hole. In those flashes, the invisible heart of the system reveals itself not through form or sound, but through the language of light escaping darkness. Around the inner edge of V404, Cygni gravity bends not only the motion of matter, but the flow of time itself, and the light that escapes from that region carries with it the imprint of both. For scientists studying the system, the timing of each photon becomes a measurement of space and time distorted by gravity. As the disk turns and the corona flares, the emission from one region echoes through another, producing a pattern of delays that can be read like sound waves bouncing through a chamber. These echoes, light reflected off layers of plasma and dust surrounding the black hole, allow astronomers to reconstruct the structure of a place that can never be seen. In this way, the invisible geometry of space-time becomes measurable, translated into the language of time intervals and energy shifts. Each outburst from the system acts as a natural experiment. When the X-ray intensity rises, light from the inner regions floods the surrounding material, illuminating the disk, the companion star, and even tenuous clouds far beyond. Some of this light scatters and returns toward the observer, with a delay at spectrum slightly altered by the gas it encounters. The time between the initial flash and its echo reveals the distance between emitting and reflecting zones, while the change in wavelength provides clues to motion and temperature. Observations of V404 Cygni show echoes separated by milliseconds, and others delayed by seconds, suggesting layers of reflection from both near and far regions. Together they form a detailed picture of the system's architecture, an inner disk of searing plasma, an outer ring of cooler gas, and an extended halo of dust shaped by previous eruptions. Light that passes through these outer regions also carries evidence of what lies between Earth and the system. The interstellar medium imprints narrow absorption lines onto the spectrum fingerprints of elements such as iron, oxygen, and silicon. By studying these lines, astronomers can estimate the amount of material between us and the source, and how it has been altered by radiation over thousands of years. The path from V404 Cygni to Earth becomes a record of both the system's own history and the galaxy's. In this way, each flare not only reveals the environment near the black hole, but also probes the spaces it must cross to reach us. Closer to the center, the echoes reveal complex movements within the disk itself. When X-rays from the corona strike, the inner disk part of the energy is absorbed and re-emitted as visible and ultraviolet light. Because the disk is rotating, light from one side is blue shifted, and light from the opposite side is red shifted. These shifts combined with timing differences produce a distinct pattern that can be modeled to determine the disk's orientation and the speed of its rotation. For V404 Cygni, the results confirm an orbit tilted relative to Earth, allowing us to view both upper and lower faces of the disk. The rapid timing of these reflections, measured in milliseconds, indicates that the reflecting surfaces lie only a few dozen kilometers apart, reinforcing the picture of an incredibly compact structure. During quiet intervals, the echoes grow faint but never disappear entirely. Even in its calmest state, the system emits low-level X-rays that interact with surrounding material, sustaining a diffuse glow that persists between major eruptions. This steady emission acts as a background signal against which outbursts can be measured, showing that accretion never truly stops. The faint reflections from this phase help trace the slow rebuilding of the disk as fresh matter flows inward from the companion star and fills the space emptied by previous collapses. These long silent intervals are as important as the bursts, for they reveal how the system prepares for its next transformation. At larger distances, the radiation from each outburst interacts with interstellar dust, creating expanding rings of scattered light that can be seen in X-ray images. These rings appear when a flare's photons encounter dust clouds at different distances along our line of sight. Because light scattered from more distant dust arrives, later the rings grow outward over time, their apparent expansion revealing the distribution of dust between us and the source. Such rings have been observed around V404 Cygni during major flares, offering not only a visual spectacle, but a three-dimensional map of the galaxy's structure along that path. The same event that signals violence near a black hole thus becomes a gentle tracer of dust and gas thousands of light-years away. The echoes also demonstrate how tightly intertwined the system's components are. When the inner disk brightens, the companion star responds within minutes, its surface heated by incoming radiation. This heating alters the star's atmosphere and can temporarily increase the flow of gas toward the black hole, feeding the very instability that caused the flare. Thus the system sustains a feedback loop. Light from the eruption changes the donor star, which in turn modifies the next episode of accretion. The entire binary acts as a self-regulating mechanism, its rhythm maintained through cycles of heating, cooling, and renewal. From a physical standpoint, the study of echoes and delays turns V404 Cygni into a natural laboratory for understanding how information travels in curved space-time. The reflections allow tests of how gravity bends and slows light, how radiation interacts with plasma, and how magnetic fields alter the direction of particle flow. The precision of modern instruments means these effects can be measured to fractions of a millisecond, providing one of the most detailed examinations of a black hole environment available. In each dataset, theory meets observation with remarkable accuracy, confirming that relativity's predictions hold true even under conditions millions of times more extreme than those on Earth. The process of observing these echoes is delicate. Instruments must capture faint signals against the glare of the primary emission, separating overlapping energies with extraordinary accuracy. To achieve this, astronomers use detectors capable of measuring both the arrival time and energy of individual photons. Each photon becomes a data point in a vast map that can later be reconstructed to show how the system changes second by second. These reconstructions reveal waves of brightness moving outward from the center, reflections rippling through the disk like expanding rings on water. Though invisible to the eye, they are clear in the data, a record of motion within a region smaller than a city playing out across the gulf of thousands of light years. Ultimately, the echoes serve as the system's memory. They preserve the timing and intensity of events that occurred years or centuries apart, encoded in the faint light that continues to reach us. By studying them, astronomers can piece together a long-term record of activity, much as geologists read layers of rock to reconstruct the history of Earth. Each new flare adds a layer to this cosmic archive, allowing comparisons across decades. The picture that emerges is one of continuity within chaos cycles of outburst and recovery, echoes overlapping echoes, light reflecting through time as well as space. The interplay of radiation reflection and delay turns V404 Cygni into a living map of its own structure. It demonstrates how light, even when trapped and bent by gravity, still carries information about the forces that constrain it. Every photon that reaches Earth has followed a curved path through space-time shaped by the black hole's mass and spin. In this sense, the system is not merely an object, but a conversation between matter and gravity, written in the language of light and time. Each echo adds another phrase to that dialogue, continuing a story that began millions of years ago and still unfolds in the faint signals recorded by telescopes today. V404 Cygni does not exist in isolation. Its eruptions send waves of energy that ripple through the surrounding regions of the Milky Way, altering the matter that drifts in its neighborhood. Every burst of radiation heats nearby gas. Every shock wave reshapes the thin dust clouds that float between stars, and every jet deposits energy that can be traced long after the flare has faded. What begins as a brief, intense event near the black hole spreads outward, affecting space on scales millions of times larger than the system itself. In this way, the invisible core of the binary leaves visible marks on the galaxy around it, connecting the physics of a collapsed star to the wider ecology of interstellar space. When a major outburst occurs, the energy release travels outward in several forms: X-rays, ultraviolet light high-energy particles, and fast-moving winds of ionized gas. These components interact differently with the environment. High-energy photons travel freely until they strike atoms of hydrogen, or heavier elements, knocking electrons loose and creating expanding regions of ionized gas. This process alters the chemical and physical state of the medium, making it more transparent to subsequent radiation. As the burst continues, shock fronts propagate through the thin material that surrounds the system, compressing it into arcs and filaments. Over years and centuries, such repeated heating and compression can create small cavities in the interstellar medium, faint bubbles of plasma that mark where energy once flowed. The jets emitted during powerful eruptions have even more dramatic effects. Moving at nearly the speed of light, they can travel vast distances before dissipating. As they encounter interstellar gas, they slow and deposit their kinetic energy, forming compact radio-bright knots that remain visible long after the X-rays have faded. These structures serve as footprints of past activity, showing where earlier outbursts once projected their force. In some systems, such relics persist for thousands of years, expanding slowly into faint diffuse clouds. Although V404 Cygni's jets are less massive than those of a supermassive black hole, they still demonstrate the principle that even small systems can influence their cosmic surroundings. Within the binary itself, the energy released during an outburst affects the companion star. Intense X-rays and ultraviolet radiation strike its surface, heating the facing hemisphere to temperatures much higher than its opposite side. This uneven heating can alter the star's atmosphere and increase the rate of mass transfer, briefly accelerating the flow of gas toward the black hole. The star's outer layers swell, its shape distorts further, and the cycle of feeding intensifies. Over time, this process may strip the star of a significant portion of its mass, gradually transforming it into a smaller, denser remnant. The black hole thus not only feeds upon but reshapes its partner, an interaction that continues until either the star stabilizes or is reduced to little more than a core. Beyond the immediate system, the radiation from V404 Cygni contributes to the broader background of high-energy light that permeates the galaxy. Although the contribution from a single system is tiny, the combined emission of thousands of similar binaries forms a significant component of the Milky Way's diffuse X-ray glow. This collective radiation influences the temperature and ionization of the galactic disk, particularly in regions rich in gas and dust. In this sense, each black hole binary functions as a microscopic engine in a network of energy exchange that links stars' gas and cosmic rays. The material ejected from the system also carries chemical signatures that enrich the interstellar medium. The gas drawn from the companion star contains elements forged in stellar interiors, carbon, nitrogen, oxygen, and heavier metals. When outflows and winds disperse this material, they seed nearby space with the raw ingredients for future generations of stars and planets. The process is slow and subtle, but over millions of years it helps recycle matter within the galaxy. Thus, even as the black hole consumes, it participates in the long cycle of creation that defines the Milky Way's evolution. Observations of the region surrounding V404 Cygni have revealed faint emission lines from ionized gas extending far beyond the binary itself. These emissions, detected in optical and infrared wavelengths, indicate that the space around the system remains disturbed long after each flare. Spectroscopic studies show that the gas moves outward at hundreds of kilometers per second, consistent with shock fronts driven by radiation and jets. By mapping these features, astronomers can trace the cumulative influence of the system over time, a history written in expanding shells and faint filaments, visible only through the most sensitive instruments. The interplay between inflow and outflow consumption and release defines the system's long-term balance. Without the outward transport of energy, the accretion disk would overheat and disrupt itself. Without the steady inward pull of gravity, the companion star would drift away. Instead, these opposing motions sustain a stable though dynamic equilibrium. Each eruption resets that balance, releasing stored energy and allowing the cycle to continue. This rhythm, repeated over decades or centuries, ensures that the system neither burns out nor falls silent. It is a slow conversation between destruction and renewal, mediated by the physics of radiation and motion. In understanding this process, astronomers have learned that black hole binaries act as scaled-down versions of the engines that power active galaxies. The same physical mechanisms, accretion, magnetic confinement, and jet formation, operate across vastly different scales. By studying nearby systems such as V404 Cygni, scientists can test models that also describe quasars billions of light-years away. The difference is merely one of magnitude. What occurs here in hours or days unfolds there over millennia. This correspondence reveals the unity of nature's design, where the same laws govern the smallest and largest structures in the cosmos. Despite the immense energy involved, the effects of V404 Cygni on its local environment are not destructive on a galactic scale. Space is vast and most of the energy radiates into emptiness. The black hole's influence fades with distance absorbed and dispersed by the medium. Yet within a few light years its presence shapes the temperature composition and motion of the gas, leaving subtle but permanent imprints. These traces remind us that even isolated systems contribute to the slow evolution of the galaxy's structure, each adding its voice to the collective hum of radiation and gravity that fills the Milky Way. For now, the system continues its alternating phases of silence and fury. Between outbursts, the surrounding space cools, the jets fade, and the dust settles back into shadow. But the memory of past eruptions remains encoded in the faint glow of heated gas and in the chemical patterns of the nearby clouds. Each new flare will refresh those marks, expanding the reach of the system's influence a little farther. Through these long cycles, V404 Cygni links the violent physics near its event horizon to the calm drift of interstellar matter many light-years away. The black hole, unseen and silent at its core, thus becomes a distant architect of form and motion in the galaxy, shaping its surroundings not through explosion, but through persistence. V404 Cygni offers scientists an invaluable opportunity to measure the invisible. The outbursts, the echoes, and the persistent low glow together create a data set through which the physical characteristics of the black hole and its companion can be inferred. Among these properties, mass, spin, and distance form the key elements that define how the system behaves. Measuring them is an intricate process that combines spectroscopy, photometry, timing analysis, and geometry. From the rhythm of its orbit to the tone of its radiation, every aspect of the system reveals something about the forces at play. Through decades of observation, astronomers have learned to read these signs with increasing precision, transforming light into measurement and measurement into understanding. The first quantity determined was mass. By observing the companion star's orbit, scientists measure the Doppler shifts in its light as it moves toward and away from Earth. These periodic shifts correspond to its orbital velocity, which when combined with the period of the orbit allows the total mass of the system to be calculated. The companion star in V404 Cygni completes one revolution every 6.5 days, moving at speeds of hundreds of kilometers per second. From these values, the mass of the unseen partner can be derived, yielding a figure roughly 9 times that of the Sun. This value exceeds the maximum possible mass for a neutron star, confirming the presence of a black hole. The companion itself has less than half the Sun's mass, a small but luminous object, deformed by its proximity to its massive neighbour. Spin, however, is more difficult to measure. It influences how close matter can orbit before falling inward, and it affects how efficiently the system converts gravitational energy into light. To estimate spin, scientists examine the X-ray spectrum, looking for subtle distortions caused by relativistic effects. When X-rays emitted by the inner disk are reflected off surrounding gas, they form characteristic iron lines that appear broadened and skewed by the black hole's rotation. By modelling these distortions, researchers infer how fast the event horizon itself is spinning. For V404 Cygni, the evidence points to a high spin rate, possibly near the theoretical maximum, meaning the black hole drags space-time around with it as it turns. This rotation enhances the magnetic processes that produce jets, linking spin directly to the system's most dynamic phenomena. Distance is determined through geometry and timing. Parallax measurements from observatories such as Gaia provide precise estimates of how much the system's position shifts as Earth moves around the Sun. Combined with data on brightness and absorption, this gives a distance of roughly 8,000 light-years. Knowing this distance allows astronomers to translate observed luminosities into true energy outputs. It also enables comparison between systems across the galaxy, placing V404 Cygni within the broader context of stellar evolution. Its location deep within the galactic disk suggests that the black hole originated from a massive star born millions of years ago, one that ended its life in collapse and left behind the compact remnant we see today. With these parameters, known models can reproduce the observed behavior of the system. They show how matter spirals inward under gravity, heats through friction, and emits radiation according to well-understood physical laws. Yet observations continue to reveal complexities that challenge these models. The irregularity of outbursts, the rapid flickering during peaks, and the unpredictable structure of the jets suggest that additional processes, perhaps magnetic turbulence or interactions between inflow and outflow, play a role. By comparing theory with the fine details of V404 Cygni's light curves, researchers refine their understanding of accretion physics, improving models that apply to systems far larger and more distant. Beyond its physical properties, the system's variability provides a benchmark for testing general relativity. Because the orbital speeds near the event horizon reach significant fractions of light, the curvature of spacetime can be probed through timing delays and gravitational redshift. When light from the inner disk reaches Earth, its frequency is shifted downward, stretched by gravity's pull. Measuring the degree of this redshift allows verification of Einstein's equations in regimes of extreme curvature. Observations of V404 Cygni consistently match theoretical predictions, reinforcing the idea that relativity remains accurate even where gravity is strongest. This confirmation, repeated across multiple black hole systems, represents one of the most profound achievements of modern astrophysics theory and observation converging at the threshold of the unknowable. Continued monitoring also refines our understanding of how much matter the black hole consumes over time. During quiet phases, the rate is small, perhaps only a few trillion tons per second, insignificant compared to the total mass of the system, but enormous by human standards. During major outbursts, this rate increases 100-fold. Over millions of years, the black hole will gain only a fraction of a solar mass, yet each episode of feeding releases radiation that shapes its environment. The process is efficient, stable, and relentless. It demonstrates how black holes, though invisible, participate in the cosmic cycle of energy, converting mass into light that travels freely across space. Measurement extends beyond direct observation. Models of the companion star's spectrum provide information about its chemical composition and temperature. The star's light, though faint compared to the glare of the accretion disk, carries the imprint of elements produced in earlier generations of stars. These signatures help determine its age and origin. In the case of V404 Cygni, the companion appears to be an evolved star once larger and more massive than it is now, stripped of much of its material by long interaction with a black hole. Its current state offers a glimpse of the binary's history, a massive star that collapsed into darkness, alongside a partner now slowly being consumed. By assembling these measurements, mass, spin, distance, composition, astronomers construct a complete portrait of the system. It is both simple and complex two bodies, orbiting under gravity, yet bound by physics that warps time-light and matter. Each observation adds a new layer of detail, refining a picture that will never be fully complete. The system's importance lies not only in what it reveals about itself, but in how it guides our understanding of all black holes. It serves as a testbed for theories of accretion, relativistic jets, and binary evolution. Through its cycles of silence and eruption, it continues to provide data that bridge the gap between human observation and cosmic scale. In measuring the unseeable, scientists transform V404 Cygni from a mystery into a laboratory. The same equations that describe the motion of planets and the fall of an apple describe the orbit of its companion star extended into the language of relativity and magnetohydrodynamics. Light captured and decoded becomes evidence of gravity's precision, and though the system lies far beyond human reach, its signals connect our instruments to the deepest laws of nature. Through this distant binary, the universe allows a rare experiment to measure the shape of space-time itself, to quantify the unseen, and to confirm that the rules governing stars and galaxies remain consistent even at the edge of a black hole. Across years of observation, V404 Cygni has revealed a rhythm that is neither regular nor random, a long alternation between deep silence and sudden brightness. These phases of calm and fury define its life, governed by the slow accumulation of matter and the swift release of energy. During its quiet intervals, the system remains faint, producing only a gentle trickle of X-rays as gas moves inward in a steady but minimal stream. Over time, the accretion disk thickens, storing gravitational energy like a reservoir behind a dam. When the flow becomes unstable, the balance collapses and energy floods outward in violent outbursts. This pattern, repeated across decades, connects the smallest fluctuations in the disk to changes that can light the sky across the galaxy. The periods of dormancy are essential. In them, the disk rebuilds from the thin stream of gas drawn from the companion star. The outer regions cool and condense, allowing material to settle into a stable orbit. Over months and years, mass accumulates in the middle zones while the inner disk remains dim and nearly empty. The pressure between these zones increases until the system reaches a critical point. A small change, perhaps in temperature, density, or magnetic field configuration, tips the balance. Once that happens, the inner disk collapses, the temperature soars, and light that has been hidden for years bursts forth. To an observer, the transformation appears instantaneous, but its roots lie in the long, silent preparation that preceded it. Astronomers have tracked this pattern over nearly a century. Archival records show major outbursts in the years 1938, 1989 and 2015, each separated by decades of quiet. The recurrence interval suggests that the time required to rebuild the disk and reach instability is measured in human generations. Between these great events, smaller flares occur, brief flickers of activity that release some energy without resetting the cycle entirely. Together they form a spectrum of variability from tiny tremors to full eruptions. The same physics underlies them all, gravity, heat, and motion combining to transform matter into radiation. Each phase affects the other. During outbursts, radiation heats the companion star, increasing the rate of mass transfer. As the disk drains, the flow weakens and the system returns to calm. The balance between these forces keeps the cycle repeating. If the companion star were to lose too much mass, the flow might cease. If the black hole's pull intensified, the system might stabilize at constant brightness. But nature maintains a delicate middle ground where periodic eruption becomes inevitable. It is a self-sustaining rhythm born of feedback between matter and energy destruction and renewal. Scientists study these cycles to understand how energy is stored and released in accreting systems. They find that the length and intensity of each phase depend on multiple factors: the mass of the black hole, the temperature of the disk, the composition of the gas, and the geometry of the orbit. In V404 Cygni, the relatively low mass of the companion star and its close orbit create a modest but steady supply of material. The rate of inflow is just enough to rebuild the disk over decades, but not enough to keep it permanently stable. The result is a system finely tuned for periodic instability, a cosmic heartbeat that continues through time. The eruptions themselves vary in structure. Some begin gradually with a slow rise in brightness that peaks over days. Others ignite, suddenly reaching maximum intensity within hours. The decay phase also differs, sometimes smooth, sometimes punctuated by smaller flares. These differences arise from the interplay between viscosity radiation pressure and the dynamics of the magnetic fields that channel the flow. By comparing the shapes of these light curves, researchers learn how subtle changes within the disk affect the observable outcome. Every outburst is both unique and familiar, a new verse in a repeating song. Between major eruptions, the system's faint emission allows measurement of its baseline state. During this time, the disk becomes optically thin, allowing observers to see the companion star more clearly. Spectroscopic data from these intervals provide insight into the star's composition and the residual glow of the cooling disk. They show that even in quiescence, the system remains active at a low level, with matter still trickling inward and radiation still leaking outward. The black hole never sleeps, it only rests between meals. The alternation between calm and fury has broader implications for how black holes evolve. Each outburst, though brief, releases a burst of energy that contributes to the surrounding galactic environment. The intervals between them determine how much material accumulates and how much is lost. Over millions of years, this cycle shapes not only the immediate binary, but also the local region of space. In this way, the quiet times are as significant as the bright ones. They set the conditions for the next transformation and regulate the long-term influence of the system. For astronomers, predicting when the next eruption will occur remains a challenge. While models can estimate the average interval, the exact trigger depends on subtle conditions that cannot yet be observed directly. Continuous monitoring with X-ray and optical telescopes helps identify early signs, small fluctuations in brightness, spectral shifts, or changes in the companion star's light curve. These indicators may precede a major flare by months or weeks, offering a brief warning of the coming burst. When the moment arrives, instruments across the world and in orbit align to capture it, gathering data from the first rising photons to the final fading glow. The 2015 outburst remains the most comprehensively observed, a benchmark event recorded by dozens of observatories. The data revealed minute-by-minute changes in brightness, confirming that the inner disk evolves on timescales as short as seconds. They also showed how radiation from the corona drives jets and winds connecting inner and outer regions in a single chain of cause and effect. This detailed picture now serves as a reference for studying other systems, allowing scientists to compare how different conditions yield different behaviors. Each observation refines our understanding of the universal principles that govern accretion and instability. The cycle of quiet and fury within V404 Cygni mirrors natural rhythms found throughout the universe. Stars pulse, galaxies flicker, and even the cosmos itself expands and cools in repeating patterns. In this sense, the black hole's eruptions are not anomalies, but expressions of a larger order energy gathering and dispersing, gravity storing and releasing. The system's alternating phases remind us that equilibrium in nature is rarely static. It is dynamic, achieved through the balance of opposing forces. As the years pass and the system moves once more toward quiescence, astronomers continue to watch, waiting for signs of the next awakening. Whether it comes in decades or in centuries, it will follow the same pattern, written into the physics of its being. Between now and then, the black hole continues to feed, quietly invisible, except to the instruments designed to sense its faintest whispers. Its light, when it returns, will again traverse 8,000 light-years to reach us another pulse in a sequence that began long before humanity existed. Through that distant rhythm, V404 Cygni continues to connect the violence of collapse with the endurance of time, a cosmic cycle, where silence builds the foundation for the next eruption of light. The long watch over V404 Cygni continues an effort spanning decades of human work and countless millennia of the system's own evolution. Today, fleets of satellites and ground-based observatories remain tuned to its faint glow, recording every fluctuation in brightness, every echo of radiation that reaches Earth after a journey of 8,000 years. Each new dataset builds on the last, deepening the collective understanding of one of the most complex and instructive black hole binaries in the galaxy. Yet despite the sophistication of modern instruments, much about this system remains uncertain. Its cycles of eruption and silence still defy precise prediction, and the underlying mechanisms that drive its sudden transitions remain only partially understood. What is known is drawn entirely from light, a steady accumulation of signals that tell the story of matter and gravity locked in endless exchange. Observations from the past decades show that even when V404 Cygni appears dormant, subtle changes continue within the disk. Variations in faint X-ray and optical emission suggest that streams of gas persist, fluctuating in strength, as the companion star's outer layers shift under its own magnetic cycles. These slow, almost imperceptible drifts may be the earlier stages of preparation for another major outburst. Monitoring missions keep constant watch for these signs, aware that an eruption can begin with little warning. In this sense, the system functions as a reminder of how much the cosmos can change in the span of a single night, transforming from quiet darkness to blinding brilliance and back again. The instruments used to observe it represent decades of technological progress. X-ray telescopes such as Swift-Chandra and Nihana record light at energies millions of times greater than visible photons, while radio arrays on Earth detect the faint afterglow of the jets. Together, these observatories construct a multi-dimensional portrait of each event. The timing precision of these instruments, measured in thousandths of a second, allows astronomers to track variations in brightness caused by phenomena occurring near the event horizon. The ability to coordinate observations across wavelengths has turned V404 Cygni into one of the best-studied black holes in existence, a laboratory for testing theories of accretion and relativity under conditions impossible to reproduce elsewhere. Despite this detail, mysteries endure. The cause of the system's chaotic flickering during eruptions, the precise geometry of its corona, and the mechanism that triggers the sudden switch from quiet to active states remain topics of research. Some evidence points to changes in the disk's magnetic field. Other studies suggest that the black hole's spin may amplify instability in unpredictable ways. Numerical simulations attempt to model these transitions, but the interplay between radiation, magnetism, and gravity is too complex for simple description. The system's behavior resists neat categorization, shifting between states of order and disorder, as though it occupies a threshold between equilibrium and chaos. The uncertainty surrounding its cycles has not diminished its value. Instead, it has made the system a cornerstone of comparative astrophysics. Every observation of V404 Cygni informs the study of other black hole binaries and active galactic nuclei. Its properties, mass, spin, luminosity, and spectrum serve as reference points for systems both nearby and distant. The lessons learned from its eruptions help explain how similar processes operate on vastly larger scales in quasars, where supermassive black holes feed on interstellar gas and power entire galaxies. By observing one small black hole closely, astronomers learn how all black holes shape the universe on every level. The future of observation lies in instruments yet to be fully deployed. The next generation of X-ray telescopes will capture even finer details of timing and polarization, allowing researchers to probe the geometry of the magnetic fields that shape the system's light. Radio interferometers with greater baseline distances will resolve the evolution of the jets in real time, following their expansion over days rather than weeks. Meanwhile, gravitational wave detectors, though not yet sensitive enough to detect binaries like V404 Cygni, may one day measure the subtle tremors of spacetime produced when its black hole interacts dynamically with its companion. Each technological step brings us closer to understanding a system that, for all its distance, remains a familiar presence in the data streams of human exploration. For the black hole and its star time unfolds on different scales. The companion will continue to lose material for millions of years, gradually shrinking as it transfers its mass into the disk. The black hole will grow by only a small fraction of a solar mass in that time, but each new addition will deepen its gravitational pull and slightly alter the rhythm of its orbit. Eventually the star may be stripped to its core, its remaining mass forming a dense ember that orbits until tidal forces tear it apart completely. Long after the last flare has faded, the black hole will persist in silence its existence, marked only by the faint trace of radiation from interstellar gas drifting too near. In this sense, V404 Cygni's current activity represents a brief and luminous chapter in an otherwise eternal story. From the perspective of humanity, the study of such a distant system is both a technical achievement and a philosophical reflection. Light that left the binary thousands of years ago arrives in the present as new discovery, allowing the modern world to witness an event that occurred before recorded history. Each observation is thus a bridge across time, connecting the formation of a flare in a distant corner of the galaxy with the quiet concentration of scientists interpreting its signals. The system becomes more than an object of study. It becomes a dialogue between human curiosity and the forces that shape the cosmos long before life began. As the observations accumulate, a pattern of humility emerges. The more clearly we measure the system, the more it reveals about our limitations, the horizon we cannot see beyond the equations that remain incomplete, the mysteries that defy instrumentation. Yet within these limits lies meaning. V404. Cygni reminds us that knowledge often comes not from direct sight, but from inference, from listening to what light tells us in its long journey through space. The data that define the system, tiny changes in brightness, delayed echoes, faint radio hum, are the language through which the universe describes itself. The watch will continue. Whether the next great outburst occurs within our lifetime or far in the future, it will once again light up the constellation of Cygnus, its X-ray flashes crossing the void like a distant heartbeat. The photons that reach Earth will join those from previous flares overlapping in the archives of observatories, another pulse in an ongoing record of cosmic motion. And when they are studied perhaps by instruments and minds not yet born, they will carry the same message they have always carried, that gravity is not silent, that darkness is not empty, and that even in the quietest corners of the sky there are stories still unfolding in the light that never truly dies.